In 2018, just 6 weeks after its grand opening, the $2.2 billion Salesforce Transit Center in San Francisco was abruptly shut down. The reason two massive multi-ton steel girders supporting a rooftop park had developed terrifying fractures. This wasn't a minor issue. It was a catastrophic failure in a landmark structure, costing tens of millions in repairs and shaking public trust. What went wrong? The answer lies buried deep beneath the gleaming facade, in a foundational assumption that proved to be a billion-dollar mistake. It's the ultimate real-world consequence of the Winkler trap we discussed in our last video. A story of how the mathematical convenience of the modulus of subgrade reaction, KS, can lead to physical disaster when it collides with extreme loads. Welcome to Strong Foundation Engineering, where we dig into the failures that build better engineers. So, what was this flawed assumption? The designers envisioned a fortress-like foundation, a colossal concrete mat between 5 and 10 feet thick, supported by groups of deep piles. This massive slab was supposed to act like a single, perfectly rigid block. Let's use an analogy. Imagine a huge, thick butcher's block made of solid oak. This block is our mat foundation. It rests on several sturdy legs, which are our pile groups. Now, place two incredibly heavy anvils on the block. These represent the skyscraper's megacolumns. The core assumption was that the butcher's block is so immensely thick and strong that the crushing weight of the anvils would be distributed perfectly evenly across all the legs. This rigid body behavior is critical because it's meant to prevent one part of the building from settling more than another, a dangerous phenomenon called differential settlement. But reality didn't match the model. The butcher's block wasn't infinitely strong under the immense concentrated point loads from the megacolumns. The mat did not behave as a rigid block. It behaved as a flexible plate. Think of it this way. Instead of a thick oak block, imagine the foundation is more like a very, very dense memory foam mattress. When you place those heavy anvils on it, the mattress doesn't sink evenly. It dimples or deforms intensely right under the anvils. This is localized flexibility. The mat foundation suffered this exact dimpling at the column bases. The load, instead of spreading out, created a zone of high deformation, fundamentally changing how the forces travel to the piles. The ability of the mat to resist this dimpling is related to its radius of relative stiffness, a concept captured by this equation. Don't worry about the math right now, just understand this. It tells us how far the dimple effect spreads. At Transbay, the load was too high and the mat's stiffness, while massive, wasn't enough to prevent this localized bending. This localized dimpling was the first link in a catastrophic chain of failure. The unintended flexibility of the mat foundation created differential settlement, but the steel superstructure built on top of it was designed to be incredibly rigid and redundant. Think of the steel frame as a perfectly crafted, intricate birdcage. It's designed to hold its shape perfectly, assuming it's sitting on a flat, solid table. But what happens if the table beneath it suddenly sags in the middle? The birdcage cannot stretch or deform to match the sagging table. Instead, the displacement is forced into the birdcage itself. Its members are twisted and bent in ways they were never designed to handle. This creates massive, uncalculated internal forces called secondary stresses. At the Transbay Center, the foundation settlement forced the rigid steel frame above to contort, inducing enormous secondary stresses in those massive girders. This brings us to the cracks themselves. When the fractures were discovered in 2018, a world-class forensic investigation was launched, led by industry giants like Lira and Thornton Tomasetti. Their analysis did uncover metallurgical flaws in the steel, specifically weld access holes that were improperly made, creating stress concentrations. Now it's easy to point the finger at the steel fabricator and say, bad steel, but that's missing the bigger picture. A metallurgical flaw is just a pre-existing weak spot. The reason that weak spot failed was the enormous, unexpected secondary stress placed upon it. The girder didn't crack simply because the steel was flawed. It cracked because the foundation's real-world settlement profile was fundamentally different from the idealized, perfectly rigid FEA model used during design. The unexpected stress found the weak link in the chain and broke it. So, what is the fundamental lesson for us as engineers? It's this: stiffness is not an absolute property. It is a relative relationship between the load, the span between supports, and the element's geometry and material properties. A 5-foot thick mat foundation might be incredibly rigid for a 10-story residential tower with a distributed load. But that same 5-foot mat can behave like a flexible noodle under the knife-edge intensity of a Transbay megacolumn. It's like a sheet of paper, lying flat. It's completely flexible, but roll it into a tight tube, and it becomes remarkably stiff and can support weight. Its material didn't change, its geometry did. The error at Transbay was assuming the mat's thickness alone guaranteed rigid behavior without fully appreciating the extreme intensity of the loads being placed upon it. The Transbay closure served as a billion-dollar reminder that our computer models are only as robust as our understanding of the math beneath the graphical user interface. We often blame the black box of FEA software for these errors, but the failure usually lies in our grasp of first principles. The software correctly calculated the result for the idealized, rigid model it was given. The problem was that the model was a poor representation of reality. This leads us to our billion-dollar question. How can we as engineers look past the software's colorful stress plots and into its mathematical core to prevent falling into the next Transbay trap? To answer that, we have to deconstruct the machine itself. In our next video, we are stripping away the flashy visualizations to perform a deep dive into the basics of FEA, deconstructing the stiffness matrix to see exactly where these modeling lies begin. Make sure you're subscribed and have notifications on so you don't miss it.